Hi, in this video, I'm going to present our recent work about light spectral estimation using variational autoencoder. And this is a work supervised by Professor Zuying and Tom Ranajat from the Electrical and Computer Engineering Department at San Diego State University. Uh, to introduce the problems that we are working on, we are trying to learn the representations of some noisy signal that we assume it to have sinusoidal representations. Uh, what that meant is that we assume the input signal can be represented as a linear combination of some sinusoidal waves, and we'll try to enhance, since they can be represented as several sinusoidal waves, this is enough. It's just to learn the frequencies of those waveforms and reconstruct the signals using those frequencies and some coefficient, which can be this AJ right here. And to learn those frequency of several sinusoidal signals, we are going to using neural network architectures which can be used in those two blocks to learn the frequency representation and also to count the number of existed frequencies. And output is some frequency estimate, which we can use to reconstruct back the signal later. So to learn this neural network architectures, we are trying to minimize the loss functions, which using the chamfer distance that comparing the true and estimated frequencies. So we propose architectures that using a neural network block called it Fourier neural operator. This is using a Fourier transform and inverse Fourier transform that is very well to learn some functional representations, and especially for sinusoidal waveform. And this block is proposed by the authors Kobashi collaborators in this reference. So we are proposing to use this Fourier neural operator blocks in the architectures called shallow FNO frequency representations. That way we have an input signal that can have several waveforms that can be having real part and imaginary part, which will extrapolate them into multiple vectorizations and then input them into FNO layers, and followed by a transposed convolutional layers to learn the frequency representations. So here is some predictions on the test data using shallow FNO frequency. Here is the blue line is the frequency representations by this shallow FNO frequency neural net. And the red is the estimated frequency, and the dotted line is the true frequency of the input signal. You can see that this neural net able to recover most of the true frequency. And in the next step of our research, we are proposing variational autoencoder architectures where we take in the noisy measurement K and we put it into this encoder, which is a frequency estimator, which could be the architecture that using Fourier neural net that we proposed in the previous slide, to learn the parameters of the coefficient alpha and the frequency omega I here. We'll use a reparametrization trick, which is common for learning variational autoencoders to learn the distribution of alpha and omega. And when able to sample from the distribution of alpha and omega, we'll use those samples to reconstruct the measurement Y using this decoder, which is just simple sinusoidal reconstructions, and to get back the clean signal Y. Thank you for listening.